So what to make of this? So we have, it's the same day of the year, the sun is highest in the sky, and a well bottom is illuminated in Syene, but not in Alexandria. So let's see what we can do with that. Let me draw a picture. And this is probably, Eratosthenes probably did something like this. So let's actually draw a horizon. Okay, so we have a horizon like so. And let's draw the two wells. So this might be one well here, deep in the ground, and we'll need a second well. So here's the second well. And we'll need the rays of the sun. So sun is straight overhead, at least in Syene. And so let's get some sun rays. So there's the sun coming down like this, and the sun like this. And on the right here we have Syene, south of Alexandria, and this is Alexandria itself. This is not what happens. Eratosthenes knew that the sun was very far away. There are other reasons for believing that. The sun was so far away that its rays were nearly parallel when it reached the Earth's surface. So this was a good picture, assuming Earth was flat. So if Earth were flat, the expectation would be that we would have, if the well at Syene were fully illuminated at the solstice, so should the well at Alexandria. So this assumes a flat Earth. But that cannot be the case. So this is wrong. Okay? That is wrong. That's the wrong picture. So let's tuck that away. Eratosthenes had another idea. Earth was a sphere, perhaps. A sphere is a wonderful shape. And it also solves the problem about where's the boundary to the Earth. There's no boundary if it's a sphere. So it's a compelling possible model. So let's actually consider a second model, a spherical Earth model. So let's see, let me draw a circle here. Circle represents the sphere in cross-section. And let's see, I'm going to need to put Alexandria and Syene in the sphere. And at your desk, you can be doing this as well. And here's a radius to maybe Syene. And then at Syene, I'm going to put in a well. Maybe something like that. It's a deep well, and of course exaggerating the size of the well. And then let's also draw in the situation at Alexandria. So at the bottom, we have Syene and its well, and then we have Alexandria up here, say maybe there. Now let's draw in some, let's do the following. Eratosthenes knew that at Alexandria, the bottom of the well was never illuminated, so actually he did an experiment. He actually put a stick in the ground, a vertical stick, and the vertical stick is an extension of the radius. And then he found the length of the shadow on the solstice. So we're going to need a little bit of geometry here. So this is one ray of the sun, and let me put another ray. Okay, so two rays coming from the sun. The sun is way off to the right. And now we have a sort of geometrical problem. Eratosthenes measured this angle, so he did an experiment, and that angle turned out to be about 7 degrees. And you notice we have two horizontal lines cut by another line, that green diagonal, and so equal interior angles from your high school geometry. So this angle is also 7 degrees. So 7 degrees is about 1/50th of a circumference. So Eratosthenes reasoned that the distance between Alexandria and Syene must be about 1/50th of the circumference of the Earth. So that's actually impressive in itself. The other thing, of course, you can see immediately the spherical Earth model solves the basic problem. At Syene, the sun can be directly overhead, while at Alexandria, it need not be directly overhead on the same day. Let's see if we can convert this into something quantitative. We can actually get Earth's exact diameter from this, or exact circumference. So we're going to need some proportions. So we can do something like this. 360 degrees is to 7 degrees as the total circumference of the Earth is to the distance between Alexandria and Syene. Now, to keep the math simple, 360 divided by 7 is approximately 50. So what we've got here is the fact that the circumference of the Earth, this is pretty amazing already, is approximately 50 times the distance between Alexandria and Syene. So Eratosthenes looked up the distance between Alexandria and Syene on Google Maps, plugged in, and oh no, Google Maps was not available. So this is actually kind of a problem. How do you find the distance between two cities 2,000 years ago? Now, historians are not sure. They did know that armies needed to march from city to city, and if you're marching an army of 1,000 men from one city to the next, you need to know how long it's going to take, because you need to know how much food to take. So they believed that there was a guild or society of professional pacers that were available. You could hire a pacer to pace the distance. Now, this is harder than it sounds. When I went to high school, I lived 2 miles from my high school, and I walked to high school every day and back. And, by the way, it was uphill both ways. That's right. But it was kind of boring, so occasionally I would try to count the number of paces from my house to my high school. I never could do it because my mind would always wander. So it's not easy being a professional pacer, but nonetheless, the distance between Alexandria and Syene was estimated by Eratosthenes to be 500 stadia. So so that means the circumference of the Earth is 50 times 500, or 250,000 stadia. Okay, well, historians have another problem now. What exactly is one stadium? It's a unit of length that's no longer in use. They think a stadium might be like the largest possible stadium, so about a tenth of a mile, or so I'm told. And so if you plug this in, this means that the circumference of the Earth is 225,000, rather, a tenth times 250,000 miles. Yes, thank you, Susan. That is exactly the kind of feedback that I need. Actually, it's wrong in my notes. But yeah, I think it's 5,000 stadia, 250,000 stadia, and 25,000 miles. So even if we're not quite right, even if we're not quite